Hello everyone, I'm Laura Lewis. Welcome to a class on RedShift. This is part of GCSE physics. We do a lot of examples in this class too, because it's the more you practice, the more you get better at the subject. Okay, so let's start with learning objectives. So we're going to look at a description of RedShift and see it in a spectrum. So looking at analysis of how we can tell if a galaxy or even a star, you'll find it later on, mainly it's galaxies, is moving away or towards us by its redshift or blue shift. And finally, a discussion of how redshift has led us to the conclusion that the universe is expanding. Okay, so what we're going to look at, I'm going to look at this one first actually. Okay, so we use a prism, okay, to split light from different stars. Okay, and if you ever use a prism to split light, okay, you'll find out that you get a rainbow, okay, a spectrum. Okay, it's the scientific name, okay, of a rainbow. And just for a moment, don't look at the letters, look at the rainbow bit for a minute. Okay, so you get the rainbow bit, but also you look at light from a star or even a light, okay, like in your house, you get what's called dark lines. Okay, and these dark lines tell us which elements are in that object. So if an object gives out its own light, like a star, okay, it would have a spectrum. Okay, so the spectrum tells us what that object is made of. So yeah, especially stars. So you might know our sun is made of mainly hydrogen and helium. Okay, but there's actually also other elements in it as well. Because the Earth and the sun share quite a lot of elements with each other because the sun and the Earth form from the same nebula. So you might look at my video on star life cycles for that bit. Okay, we're going to focus on redshift today. So what will we look at? We look at an element in a lab. So this example could be hydrogen in the lab. We'll just take it as that for a minute. The example, we could be looking at hydrogen. So we're burning some hydrogen in a lab on Earth. We're just literally burning it in a flame. We're splitting the light with a prism. So this glass object, sort of like prism shaped. I was going to say that the shape is named after the object, prism shaped. And it splits the light, and you see these dark lines. They're called Balmer lines, actually, on the spectrum. Okay, the science of doing this is actually called spectroscopy. So you may see that word in your exam, spectroscopy. Okay. So this is example. This could be hydrogen. You don't have to remember, okay, all the lines, okay, for exam, because they'll give you a diagram. You just have to know how to do it. So in general physics, there's not usually that much to remember. You just remember the method. That's why we're going to lots of examples today. It's more about the method. There's not many facts to remember. It's the way you apply it, okay, in physics. And that's my degree was in astrophysics. And yeah, I don't have to remember that much. It's just the method. Okay, right. So this is laboratory reference, we call it. So on Earth, sitting still, if we burn hydrogen, we get these dark lines. Okay, so this tells us each element will have different dark lines. So I'll quickly flash back to that. So each element will have a different pattern of lines. Okay, we'll talk a bit more about that in a minute. So each element has a different pattern of lines. Okay, so we got this in laboratory, and then we looked for all stars contain hydrogen, so it's a good thing to look for hydrogen. We might start out with that. Okay, so star. Okay, so we're looking for the hydrogen lines, they match up, but they're a little bit moved over here. Okay, right. So just for a minute, just have a look at the pictures for a minute. A nearby galaxy. Okay, so this moved a little bit further over. Distant galaxy, everything's moved this way. Very distant galaxy, this line's completely disappeared. It's moved so far over, it's disappeared. Okay, so these lines are moving towards the red end of the spectrum. Okay, so the whole effect, okay, is called redshift. So that's where the word comes from. It's as simple as that. It's because the lines are moving in the direction of the red part of the spectrum, so they're moving that way. Okay, so if you look at this now, the wavelength, right? The letter for wavelength is lambda. It's a Greek letter, wavelength. And it goes from 400 in the blue all the way to 700 in the red. So red light has a longer wavelength than blue light. Okay, and violet light's even got a shorter, but we'll say blue and red just for the minute. Okay, make it a bit easier. So yeah, red light has a longer wavelength. So red light, so I'm going to say it again, red light has a longer wavelength than blue light. Okay, so these are moving towards the red end because the wavelength is increasing. Okay, so star, galaxy, distant galaxy, the wavelength is increasing. Okay, so example, we took these double lines here. It's quite distinctive, aren't they? That they're increasing in their wavelength. So relative to each other, they're not changing, but all of them and their friends here are moving to the right, moving to the red end. So they're being red shifted, so that the more distant the object is, the more its light is being red shifted, and the more its light is being stretched out. Okay, so it's moving away from us. So think of it like on a slinky, like being attached to like one attached to our galaxy and another touch. It's like it's stretching it out. Okay, it's stretching as an object moves away from us. It's stretching the light out more, becoming red shifted. Its wavelength is increasing. Okay, because red light has a longer. I don't keep saying it's very important. Red light has a longer wavelength than blue light. Okay, and the more it's red shifted, the faster it's moving away from us. Okay, it's as simple as that. So the more it's red shifted, the faster it's moving away. So a nearby galaxy is moving away from us, but is a little bit redshifted. Distant galaxy, more redshifted. Very distant, it's completely gone off the chart. Okay, so yeah, the further away the object is very key as well. The further away the object is, the further away the galaxy is, because generally we talk about redshift, we can talk about some stars, that is true. We generally talk about galaxies. The stars are something a little bit different because they're a bit more local, so they're a little bit, yeah, they're very more subtle. But galaxies are very, very clear. Okay, and galaxies, they're all the galaxies apart from some very nearby ones like Andromeda, because we're in the Milky Way galaxy. They're all moving away from us, and they're all moving away from each other. Okay, so that's a very fundamental idea that was discovered. Okay, that all the galaxies are moving away from us. Okay, and they're also moving away from each other. Is another key point there as well. So what can that? So let's have a look at this diagram. So this is just showing that each element has got its own, it's called like signature. So it's got its own set of lines. I mean, I always remember this sodium one. Sodium is in street lamps. Okay, it's got these dark lines, sorry, on the yellow bit. So you can see why sodium lamp is orangey yellow, because it's doing something very important. Okay, so it's something emitting light in this yellow bit. Okay, so you can tell a sodium lamp. But yeah, each element's got its own set of signature lines to it. And an interesting thing is that when scientists first looked at the spectrum from the sun, they found a set of lines they didn't recognize. Okay, so they'd never burnt on Earth. It was actually helium. Okay, so helium was discovered in the sun by its spectra before it was discovered on Earth. Okay, so it's the word helium comes from the word helios, meaning sun. You might know helium from things like party balloons. Actually, it's quite hard to make helium. It comes from the radioactive decay of uranium, so alpha decay of uranium. It comes from, and helium doesn't stay on Earth very long. It's very light, and if you let a helium balloon down, the helium from that balloon will go up in the atmosphere and escape into space. Okay, it's so light. Okay, so another very key point, okay, about this would be the recessional velocity of a few galaxies plotted against it. So this is Edwin Hubble's work. Okay, so it's distance away. So these are all galaxies. So say for example, we could do this ourselves. We could plot all of the distances. We use stars to do that. Okay, so that's a different thing. We use stars to do it. And look at how fast they're moving away by their redshift. And the further the galaxy, the faster its motion away from us. Okay, so this led to the idea that the whole universe is expanding. Okay, everything is moving further away from each other. It's kind of, it doesn't have an example. So we'll see in a minute, we'll see an example where there's a balloon being blown up. So if you've got a balloon, and drew a pen on it, okay, and then blew it up, all the points on the balloon would move apart from each other. It's like that. And you would say, where's the center? And it's like, well, it actually has no meaning in the universe where its center is. So yeah, that's a good question. Obviously, it's a very valid one, isn't it, about where the center is? But there's no physical meaning for its center in our universe, as we know of yet. All these things are being developed. All ideas are being developed all the time for things like this. It's a very exciting sort of field to keep up with. But we know for the moment that it's expanding. Okay. So let's look at some questions. So a bit of a review. Yeah, there's quite a lot of information here. So let's put a text box in. Insert text box. So it says so these are all questions from an exam. In 1929, that's quite a long time ago. One of my grandparents might have been alive then. The astronomer Edwin Hubble observed that a light from galaxies moving away from us, moving away from the Earth, that's the same as us really, had longer wavelengths than expected. What is the name given to this effect? We know now it's redshift. Okay, 1 mark, easy. Okay. Then we get his graph that we just looked at. Okay. From his observations, Hubble was able to calculate the speed of a galaxy and the distance of the galaxy from Earth. It's a very important exam question, always to read it. Okay, read it carefully, because sometimes anyone can make the mistake of answering the wrong question. Okay. So figure 1 shows the results of Hubble's calculations. So when you look at a graph, you always look at the axes. So speed of galaxy away from the Earth in kilometers per second. Okay. So it's very similar to the graph we just had. Distance in kilometers. Okay, so these are very big distances because they're galaxies. What relationship between the speed of a galaxy and the distance suggested by Hubble's results? So now, what looked like maybe a complicated question, it's actually very easy, isn't it? Okay. So some obviously were anomalies. I said that they don't all follow, but in general they do, because some are nearby galaxies that are might be moving quite as far away. Okay, or there could be different motions, but generally we're talking about. So the more distant the galaxy, the faster it is moving away from the Earth. Okay, so we got an extra bit. This led to the idea that the universe is expanding. Also, there's if you draw a line through it, which we'll see another question, if you draw a line through that, it goes to the origin. It goes to the 0 point. Okay, so that means that the universe, okay, with our data, started from a 0 point. So it started from nothing. So that's what the Big Bang Theory is based on. There could be another video based on that, but this is where the Big Bang Theory comes from. Okay, is that this has a starting point. Okay, done that, I've done that. Okay, there's the balloon. Okay, I'm talking about. There's 2 parts to this question. Okay, let's have a look. So the observations made by Hubble support the idea that the universe is expanding. Oh, we just said that. We already jumped the gun there, didn't we? We already said that means that. This means that galaxies are continually moving away from each other and from the Earth. Yeah. Figure 2 shows a student using a balloon to model the idea of an expanding universe. So some dots which represent galaxies are marked on the balloon. The balloon was then inflated. So it says give 1 strength and 1 weakness of the model in representing the idea of an expanding universe. So let's do a text box again. Okay, so strength, so straight away, because I compared it to a balloon straight away. Okay, so strength, all of the dots, which we might draw on the balloon, like with a pen or something, which represent galaxies, are moving away from each other. Okay, it's only 2 marks this question, so I think too onerous. Weakness. Okay, so it depends on how he's blowing that balloon up. I guess it's constant. So the weakness is that in the real universe, let's write this down. In the real universe, the further the galaxies are from each other, the faster. So we can't really replicate this on the balloon. The faster, because the universe is accelerating. So faster the galaxies are moving, which is not represented in the balloon model. So this is a good thing about the word model, because it doesn't always represent exactly real life, does it? It tries to sort of emulate little bits of it, but it doesn't always emulate the whole thing. Okay, more practice. In the 1950s, there were two main theories to explain how the universe began. Theory 1, the universe has always existed and is continually expanding. New galaxies are formed as older galaxies die out. That one's called a steady state, that one. So theory 2, the universe began from a small region, so like a sort of small little point, that was extremely hot and dense. The universe has been expanding ever since. So that's a Big Bang, isn't it? Okay, actually, originally the Big Bang was named that because someone actually was denying it. Okay, it was a scientist on a radio show, and they were saying, they were kind of mocking it. They said, oh, like some kind of Big Bang, and it kind of stuck. And it's quite funny. It's quite a funny thing, isn't it? That it wasn't named that officially. It just came to stick, really, isn't it? But okay, so let's have a look then. In what way did the observation made by Hubble, so the exams use a lot of his data, support both theory 1 and 2? Okay, so there's only one thing, isn't there? They have in common. The data collected from Hubble shows that the universe is expanding. This supports both of the theories. Maybe 1 mark. Okay, most scientists, there's always another bit, isn't there? I think there's nothing more than 1 mark here. Most scientists now believe that theory 2 is correct, so the Big Bang. Suggest what is likely to have caused scientists to think theory 1 is wrong. I'm going to give you 2 things here, okay? So the data from the Hubble, do you remember it showed there was a 0 point, I pointed out. So that's one thing. Okay, let's put a text box in. So the Hubble data still shows, doesn't it? Shows that the universe started from a point. Okay. Also, there is, it's not really that covered in this lesson, but I'll talk about it anyway for a bit. There's radiation left over from the Big Bang called the cosmic, it's another video, cosmic microwave background radiation. Often shortened to cosmic CMB, so CMBR. Okay, as you might see it like that, it's all the same thing. Okay, because there's been discovered a cosmic microwave background radiation, but it's also, it started from a certain point. So I've given you 2 bits. I know it's only worth 1 mark, but I've given you 2 bits of information you could use there. Okay, so we've got an actual diagram of redshift now. So scientists can use the visible light spectrum from distant stars to determine whether the stars are moving. The visible light spectrum from stars includes dark lines, yet the Balmer lines, okay, at specific wavelengths. The diagram shows the visible light spectrum from the sun. So we're assuming we're not really moving that fast relative to the sun, other than an orbit, but we average that out, we take account. The diagram shows the visible light spectrum from the sun and from other stars A, B, and C. Okay, A is kind of gone that way a little bit. This one's gone that way. So something can actually go towards a blue and be called blue shifted. So that means it's moving towards us. Okay, it's less common, but it does exist. That's red shifted and that's blue shifted. So how does the speed of star B compare to the star D? So D is more blue shifted, so it is moving towards us faster. Okay, so D, speed of B is less than star D. Okay, also that I would put in there that it's moving towards us as well, if I was the examiner. Okay, but only 1 mark. So yeah, the more that something's shifted, the faster it moves. It's exactly the same as galaxies, but just the other way. Okay, the Big Bang Theory is one theory explaining the origin of the universe. The graphs X, Y, and Z show how the size of the universe may have changed over time. So start of time, time running, size of the universe, all the same, that one. Size of the universe, time getting bigger, starting from a point, remember that's important. And this one, size of the universe, start of time, it starts off at a certain size, okay? So which graph with the Big Bang Theory suggests is correct? So it's this one. It's B, so let's put a text box in. Explain the reason for your answer. So let me just change it to no opaque background. Shape format. Okay, so I can write in it. Okay, so figure. So you get 1 mark for saying the right one anyway. So figure or graph. You can call them a figure actually, but I'll say graph because I call it a graph. Graph, X, Y. Okay, so X, Y, and Z, like that, graph Y, so the second one, shows the universe starting from a 0 point, okay, as it needs to be to refer to the graph a bit, as the line crosses the axis, okay, at 0, 0. Okay, so this supports the Big Bang Theory that the universe started from a single point. Okay, also graph Y shows I put graph B instead of graph Y. Graph Y, the graph Y shows that the universe is expanding over time, which is consistent, that's a good word, with the Big Bang Theory. So expanding and starting from a point, okay? The main points there, okay? Okay, so now we've got a little bit more advanced where you use a star. Yeah, I found this because they use a star instead of a galaxy or something, which is fine. They can do that. So it's more unusual, but you can do that. So many stars are part of a binary system. Binary star systems have 2 stars, star A and star B, and they rotate around a point. So some stars, like one will rotate around the other. Different ways you can do it. The visible spectrum from stars includes dark lines, like we said before. These lines are at specific wavelengths, okay? The diagram shows the position of 2 dark lines in the spectrum from the sun. So we assume we get the sun, we're taking it as a reference. It also shows the same lines in the spectra from 2 stars, A and B, in a binary star system at the same point in time. So we take it like a snapshot. So this is increasing wavelength. This is the red end. So it's increasing wavelength, it's red. So star A, slightly redshifted, just slightly, because stars would be a smaller effect, but they can show them. Star B is blue shifted. Okay. So what name is given to what name is the effect shown in spectrum from star A? So star A is redshifted. Okay. So even just knowing some words gets you some points in physics. Okay, redshifted. Only 1 mark, just 1 word. Okay. Redshifted is fine. Okay. And this one, scientists have included 2 stars in a binary star system, so this one, okay, orbit around a fixed point between 2 stars. A comparison of the spectra between from the 2 stars in a binary system provides evidence to support its conclusion. But this is actually quite complicated. That's why I included it here. I thought it was a very interesting point. Okay, so again, let me just fill in the shape. Text box, a bit of IT as well. Okay, so star A, okay, is redshifted. So star A is redshifted. This means that the star is moving away from us. Okay. Star B is blue shifted, which means the star is moving towards us. The light squashed. If one star is moving away and the other towards us, they must be orbiting a fixed point. If they didn't show different wavelength changes, so one star could be orbiting the other. So if one showed a shift and the other one didn't, it means one star's moving, but they're both moving around a certain point. That's quite a difficult idea. That's why I included it here. I saw that question in the exam and I included it here. Okay, so I think they've even got the diagram, haven't they? Yeah, they're showing it. They're showing you in case I think you didn't get the point. They're trying to help you by saying that that is what they're doing. Okay. And then last question, we'll finish off with this, is Big Bang Theory uses redshift as evidence to explain the beginning of the universe. How does redshift from distant galaxies provide evidence for the beginning of the universe? Okay, so talk about Hubble data. So the distances of the galaxies away from us and the speeds of them can be plotted on a graph to reveal a relationship between the distance and the speed they are moving away. Okay, just explain redshift for a minute, actually, just in case for marks. The redshift is the increasing of the wavelength of spectral lines, the dark lines, the Balmer lines, spectral lines relative to a laboratory frame. Okay, so if the data is plotted and a line of best fit drawn, the line goes through 0, 0, like we said before, meaning the universe had a beginning and started at a 0 point. Okay, so need these 3 things, okay, to get the 3 marks. So thank you for listening. Hope you enjoyed this video. I enjoyed doing this one. Hope to see you in another class. Thank you and goodbye.